So, Engamana, Engareo, Raurangatirama, Tenakoto, Tenakoto, Tenakato, Katsua. Kia ora, ko Giovanni Russello toku ingoa, kei rotu au ite School of Computer Science. So, ladies and gentlemen, boys and girls, my name is Giovanni Russello and I'm the head of the School of Computer Science here at the University of Auckland. So, welcome to this third lecture of the Gibbons series on AI in society. Before introducing the speaker for tonight, a bit of housekeeping. So if you are looking for facilities, there is one just out there at the door on my right hand and one at the end of the hall. And in case of any emergency, if you see us running, follow us. By the exit out down there. So we might be actually following you. So tonight is a great pleasure to introduce you to Dr. Yun Sing Koh. Yun Sing is a senior lecturer at the School of Computer Science here at the University of Auckland. She completed a PhD from University of Otago. There is a kind of pattern here. Not that we are doing machine learning, but and she's been working at the University of Auckland since 2010. I need water. That's before joining us at the University of Auckland, she was working at IUT for 3 years between 2007 and 2010. So obviously, she's working on machine learning, and you're going to know a bit more about what the specific area that she's researching. And she's published more than 100 research papers on top conference in her field. So the title for the talk today is Learning to Adapt to Changes in this Dynamic World. And I think it's very topical. So with, I think, COVID, one of the things that we have learned is that we need to be able to adapt and switch to different way of conducting our life, let's say, and also in a very short notice. So let's hear from Yun Sing how machines are able to adapt and cope to a changing world. And please, Yun Sing, the floor is yours.
Thank you, Giovanni. Thank you, Giovanni, for your kind words. Kia ora koutou katoa, ko Yun Sing Koh toko ingoa. Good evening, everyone. My name is Yun Sing. So in terms of the title today, one thing that I would like to clarify is that I actually gave Jill my title prior to me knowing what 2020 was looking like. So I apologize if this title seems to be a little bit offensive. So over the past decade, machine learning has evolved from a field of lab demonstration to a field of viable commercial studies. It's used in different applications, from virtual personal assistants through to email and malware spam detection, through to online fraud detection, and even through to what you buy, product recommendations. It is a pivotal time for us to consider the viability of maintaining these models. So in this session, I will discuss how we develop machine learning models really quickly. I'll also talk a little bit about some of the concerns we have when we are faced with data that's changing. Then next, I'll share some of the fundamental ideas of how we capture and adapt to change. And finally, I will end with one specific example of current research that we're doing. So the way machine learns is very similar to humans. We learn from experience. And the more we know, the more accurately we can predict the future. So by analogy, when we're faced with an unknown situation, the likelihood of success is actually lower. Similarly, this is similar in machine learning, whereby we are training these machine learning models based on some historical data. To make an accurate prediction, these machine learning needs to actually have seen these examples previously. So when we give the machine a similar example to what has seen previously, it can figure out the outcome quite accurately. However, like humans, if it's never seen examples before, these machines may have difficulties in predicting. So I'm just going to run to a very simple example of how we train a machine learning model. So the core objective of machine learning is in two parts. First is the learning part, and the second is in the inference. First of all, machine learns through the discovery of patterns. So this discovery is typically made from the data that's given to it. One crucial part of the process is to carefully choose what data it sees. So give a very simple example. Say we want to model credit default risk prediction system. So you want to actually figure out whether a customer will default on their loan or not. So the data that's given here particularly would be a customer database. And this particular customer database will have historical records of previous customers. And in that particular record, for each customer, it will have specific attributes. This attribute can be things like age, salary, occupation, etc. Now, from that list of attributes, what we want to actually get is a vector, or a feature vector, as we call it. Now, this feature vector is what we are using to actually model our machine learning. You can think of these feature vectors as a subset of the data that's being used, and that's used to tackle specifically the problem. So the choice of the features is actually pretty important, because if you do not choose the right feature, you're actually modeling the wrong thing, and that's not a good thing. So another specific variable that you're typically given is what we call a target variable, and that's the outcome. So in the credit risk default system, historical data, each customer might have a label associated with it, and that's specifically a ground truth, saying whether that person actually have previously defaulted or not. With both the features vectors and the target values, we can actually use machine learning to transform these into a specific model. So we parse these features through an algorithm, a machine learning algorithm. It could be a deep learner, it could be the decision tree, it could be a logistic regression. And on the other side, you actually have a model that's built based on the data that's given. Once you've trained it, you make sure that you validate it, and once you're actually happy with it, what you do is you sort of let it go into the wild. And then what you do then is, as more data comes in, you parse it or you transform the data into the right feature vectors, you push it through the model, and voila, you get an outcome. So for the simple case of the credit default system, you actually see whether when a new customer comes in, you can actually figure out whether they will possibly default or not. And the caveat here is that the data that's actually been passed through the training and the data that you're using currently are actually from the same population. What do I mean by that? It means that they have similar attributes. They are similar in terms of the properties that they have. So one thing that's very clear, if you don't have the data that's from the same population, your model may not be able to give you the right prediction. So for example, there was an MIT technology review recently in May, and the title of this review was "Our Weird Behavior During the AI Pandemic is Messing with AI Models." What is clear is that this COVID pandemic has revealed how intertwined our lives are with machine learning models. And it exposed a very delicate codependence between our human behaviors and the machine learning models. So generally, this is kind of a reminder that even with an automated machine learning model, there are sometimes we have to keep an eye on it. So let's take in terms of these machine learning models, what do we want from it? We want it to be agile enough to continuously learn. In turn, when we actually deal with real-time data or streams of data that's coming in. Data streams or these kind of data may change to different factors. It could be environment factors, which might be implicit, just personal choices, customer choices, or there might be a dramatic external reason why things are changing, like a catastrophic event, like the pandemic. These changes will degrade or possibly may degrade the predictive ability of the models built. Specifically, when the data that you've actually trained and tested it on is no longer valid or obsolete. So I'm going to take a look at an example of when this has happened. And let's take a look at how the pandemic had an implication on what we buy. So in terms of February this year, what we can actually see is that the top 10 searches on Amazon were things like toilet paper, face masks, hand sanitizers, paper towel, Lysol slates, so on and so forth. These kind of things you would never thought of actually being top 10 searches last year. So last year it was things like handphones, AirPods, Legos. Those were top 10 searches. But this year it's completely different. And on the graph right on the right-hand side, what we can actually see is how we track COVID pandemic by what we shop for. So in this particular example, each of the line here represents a country. And on the y-axis is the number of top 10 searches on that list. And on the x-axis are the dates. What's clear here is that the spread of pandemic started from, it looked like it started from Italy, Spain, France, Canada, and then UK and Germany was at the back. So that's actually pretty interesting. But the interesting thing that we have to realize is that these changes here not only affected a recommender system, but it also affected a lot of other machine learning models in the ecosystem. Think about it in terms of machine learning models when you're actually dealing with inventory management, if it had machine learning in it, or fraud detection, marketing, much more. All of these machine learning models that were dependent on the data being correct are now no longer so. So things change, and we need to be able to adapt. So models are trained on what we consider normal human behavior. And if the new norm doesn't look like what it used to, then we have to start shifting the models. Let's take another look at how this illustrates, how these changes can be illustrated in terms of shifts within models. Now, this particular data set is of a New York City motor vehicle collision. And this is quite a good data set that's been collected since 2017. What's been collected is the number of collisions, which is on the y-axis. And on the x-axis are the dates. If we wanted to build a model from this, we can simply do so. This is an example of when we actually use machine learning, specifically for this one, an LSTM recurrent neural network was built. The data that was passed into this was 120 days of data prior to December 2nd, 2019. What the model that came out allowed you to actually forecast ahead of time, 22 days. So under normal conditions, what do we see? Now the green patch there is the predicted outcomes, and the blue line there is actually the actual observation. It's pretty accurate. It's actually pretty close within a confidence. Now, let's take a look at what happens if we actually use the same model under COVID pandemic. So what we can see here is that, well, the model still predicts. It predicts at the normal range. But what we see here now is the blue line. The blue line is the actual observation, and it's a clear marked difference between what's actually predicted to what's actually has happened. So we can actually see how dramatic these changes, or what we call drifts now, impact or the forecasted accuracies. So in terms of the data, let's talk about the data a little bit. what type of data are we actually sort of looking at? So we want to actually look at data that are streaming. And why is it streaming? Because there's a couple of things that is interesting about these kind of data. It comes in from continuous flow of instances. So it's rapidly coming in. It's unlimited in sizes, which just means it's unbounded. And then there is the possibility that these data might have changes in its underlying distribution. It might evolve over time. Typical example of streaming data is things like sensor data. You can also have it in data that's collected from traffic management and recommender system and a whole lot more. Most of this data has a time component to it. In terms of detecting changes within this kind of data, there are 3 specific types of changes I like to talk about. The first is what we call a specific type of change, which is called concept drift. When we have concept drift, there is a shift in the relationship between the features going in, which are independent variables, and the target variable, which is the label. So sometimes, if you think about it in terms of our purchasing behavior, when we used to, pre-COVID pandemic, when we go to the supermarket, we typically buy eggs, milk, toilet paper. Nowadays, we go to the supermarket, we buy Lysol, Dettol, toilet paper. So there is a different marked change between our behaviors in terms of what we buy. The second type of drift that I like to talk about is virtual data drift, or what we call covariate shifts from statistical domain. And these are statistical properties of input variable that these have changed, but they don't really lead, possibly do not lead to relational shifts. What I mean by that is, for example, if you think about it, in summer, you might go and buy jandals, which is things you wear on your feet. And then you might also buy sunblock, right? So that's because it's summer, you want to go to the beach. And sometimes, and the frequency is quite high. And in winter, typically, in a normal year, you might buy those same things. You buy jandals and you buy sunblock because you're preparing to go on a vacation. Of course, this year, nobody's going on vacations anywhere. So in terms of that, that's kind of a different type of change. Now, there's a third change that we have, which is called upstream data changes. What does that mean? So this means that the encoding of these features might have changed. So for example, if you encode temperature, you might have started encoding in Fahrenheit. Later on, you start encoding it in Celsius. This means that you have dirty data now because they're on different metric systems. Now, in terms of other things that might change is new features that were added. So for example, imagine a sensor network. And halfway through your data collection, you might end up adding an additional sensor. So that might skew your data. Or you might end up actually losing a sensor because one is broken. So you decide that take it out of your network. This means that this will lead to missing values as well. All these changes will actually impact your machine learning models. So in terms of the goal of streamlining, we want to be able to maintain these models. And what we mean by maintain these models is that we want to actually be able to actually have them online to make sure that they can actually still produce results at any one point. But then you will also want to update them incrementally so they're actually accurate. Typically, they're single pass because if we remember, data streams come in an unbounded format, which means that it's continuous, it's infinite. You don't have the luxury to actually traverse the data multiple times. You might have limited time and memory to do it as well. So for example, I understand that nowadays there is a lot of systems that can store a lot of data, but these systems are still bounded. And typically, when we're dealing with data streams, it's still considered unbounded. And the last but not least, is we want to be able to have anytime learning and anytime queries as well. So at any one point, we need to be able to actually ask the system, and it can give us a somewhat accurate prediction. So there are different property of changes here now. Well, I'm talking about the characteristics of these changes. So there are the ones that are quite sudden, where you have one model that shifts to another model. So in this particular example, you have AirPods, and then there is, it shifts to toilet paper. That's one example. And then we have the other ones, which are more gradual. That means one concept comes in, and then they have the second concept, and then the first concept comes back in, and then you have slowly transition from one concept to another concept. And the last one is what we call recurrent drift, which means that it's basically because of seasonality or periodicity, where you have one model that shifts to the second model, and then the first model comes back in, and then you end up with the second model, and so on and so forth. So there are different types of drifts, and the reason why we care about the different types of drifts is that depending on what properties they are, it might actually influence what type of technique you use. Whether you want to actually monitor it and decide to change entirely, or whether you want to actually ensure that it has a smooth transition across. So how do you detect and address these changes in data streams? So there is a couple of ways we do it. Now the first way is the classical way, which we call monitoring. So in terms of monitoring, there's different things that we can monitor. We can actually monitor the data itself, which means that we're monitoring the distribution of the incoming data or the distribution of the target variables. You can monitor the features itself if we want to. Or you can actually use the model as a proxy and monitor that. When we talk about monitoring the model as a proxy, what do we mean? We're saying that we're actually looking at the error rates or accuracy of that specific model. When the accuracy drops below some sort of threshold, normally bounded by a statistical property, we say that the model has shifted enough for us to be concerned, and we might want to actually reevaluate the model or take particular actions. Then you have the second type of update, which is what we call an online update. So in an online update, what we want to do is incrementally learn a model or a classifier to be as accurate as if it was carried out offline or a batch mode. This allows us to have a smooth transition between concept shifts. Otherwise, sometimes there might be situations where you have sharp degradations in the middle. So we want to be able to continuously monitor these changes. And then the third way of actually detecting changes is actually making sure that the data that's coming into your model is correct in the first instance. What this means is you might be able to detect and correct upstream data problems earlier, for example, dirty data. Or you might want to actually ensure that your parameters that you're using is actually within the reasonable bound. Most machine learning models comes with some parameters that you have to set. And this is very important because a good set of parameters ensures that you have a good model. A bad set of parameters would not allow you to have the similar type of prediction. And then further on, there is also the type of shifts that we may see is when we have drift or deterioration within over time as well. So imagine you have sensors. There is monitoring, let's say, air quality or water quality. These kind of sensors generally are really good, but they might deviate over time in terms of the readings. Depending on, when I say very good, it depends on which sensor you're using. It might deviate over time when you're actually producing the readings. So it might have slight degradation over time, or it might increase. So the values aren't continuously correct over time. So you might actually, if you see this kind of problems, what you might need to do actually have some sort of function estimation that you actually put on top of the data to correct it before it goes into your model. So in terms of monitoring, this specific data feature extraction, classifier, prediction, we've seen this. This was the similar pipeline that we've seen when we actually are doing an inference in a model. So when data stream comes in, we can actually monitor the changes within the data. We can actually monitor the changes within the features. We can actually monitor the changes within the prediction. And we can also use the proxy of the accuracy, which actually what we're typically doing is we're actually matching our target variable to our prediction. We're predicting our real ground truth to what we're predicting, sorry. And we're monitoring how accurate that is. If it's not very accurate, then we actually start signaling a drift. So in this monitoring, we can actually divide that into two parts. There is the change detection that detects whether something's changing, and then there is the adaptation part. It depends on how you want to adapt now. So that's the first type of change. This is what we call an explicit system, where we're explicitly signaling there's a change. And then there are the ones that are what we call implicit systems, where same pipeline, we have an estimator within the model itself. And this estimator actually allows you to actually check whether the shift has happened. Now, a very elegant online modeling technique is, that's been used in data streams is called adaptive random forest. Adaptive random forest is derived from random forest, which is a classical technique in machine learning. And what it does is, in random forest, it consists of a large number of individual decision trees. And each of these decision trees operates as it gives you a result, and in the forest, it actually collects the results collectively and votes. And from this ensemble, you get a decision from that. This is what we call, when we do this is what we call wisdom of the crowd. We're trying to actually collectively figure out what that one prediction is. Now, in terms of adaptive random forest, instead of having a data stream coming in and you have different trees, what are we doing? We are, in each of these trees, right here, we have a drift warning detector internally. And when a drift warning is signaled, it sort of says that our data is starting to shift. So if your data is starting to shift, it's sort of a precursor to that would be, or a reaction to that would be, all right, we have to start building backup trees. We don't really know yet whether there's a shift, but we sort of think there might be a shift, so we start building backup trees. So these backup trees actually are trying to capture what's happening in the stream at that specific time. And when we actually signal a drift internally in that particular tree, we say, all right, that tree is no longer quite valid. We then replace the background tree into the ensemble. We start using it to predict. So this is an online adaptation. It's very elegant. Now, there are various challenges in dealing with concept drift in the real world application. So there's a couple of things that we want to be able to do. One is, how do we develop online systems that ensure reliability of any updates? Because realistically, it will be worse that you actually continuously update your system and it fluctuates all over the place and doesn't really give you, that will actually be a larger penalty on your machine learning model outputs. The other thing is understanding what type of drift has occurred. Because if it's a real concept drift, then we might want to shift our models. If it's a virtual drift, shifting your model doesn't actually gain you much more, because it's actually not a relationship change. It's not what we call a decision boundary change. So we really don't want to be shifting when you don't have to. So an example of a particular work that we've done recently is called Calibrated Concept Drift Detection. And I'd like to credit our student, Hamish, for this particular work. And this particular work was funded by Precision-Driven Health. So when a patient is referred, in this particular premise, when a patient is referred to a specialist medical facility, there is referral documents that's actually sent through from the GP to the medical facilities. It could be structured, it could be lab tests, it could be information about demographics. And from that documents, the clinicians or the specialists will actually make a decision on how to triage your case. So whether it's a priority, and it could be anything where from 1 to 5, where 1, they say we have to see you immediately, 5, you're actually at a lower priority. So that's the particular setting that we're dealing with, of how we've come up with this drift detection problem. So first of all, we have our general practitioner. They produce a referral, goes to a clinician, they produce a triage label. And from this point onwards, what happens next is that with this base learner, what we want to actually sort of generate a base learner or a model to actually triage these priorities. And this comes from a bunch of historical documents of referral documents and the triage priorities. And what we want then next is to be able to provide a decision support to the clinicians. Now, the critical thing here is this is not to replace the clinician, but more of the ability to prioritize what cases gets triaged first, or some sort of priority list potentially. That's the use case of it. But one thing that we have to be careful about is when are the predictions continuously correct. So we want to monitor these predictions. So we get the true labels, and we actually sort of look at it, which is the true label is actually the triage label by the clinicians. And then we want to actually sort of pass in what's the predicted value. And then we have a detector there that actually sort of tells you when something has drifted. So if something has drifted, then what we do is we say that the model itself has to be retrained. Now, there is several special requirements here. We want to actually have a low false positive because unlike normal data streams, the data that's coming in is not like 1 million inputs per minute. They're actually the frequency of it is relatively low. But by contrast, what we care more about is that we are not causing unnecessary retraining, and we're promptly detecting changes as well to avoid errors. So in terms of this, there's a couple of things that we care about. So when we learn a model, particularly you get it to predict something. And when you get it to predict something, it's normally a binary output. It's yes or no, you predicted correctly or you didn't predict it correctly. There's another element to this, how confident you are in your prediction. Because that actually makes a difference. Because you can build a model, and the next question, for example, a simple example is, if I asked you, is it going to rain tomorrow? And then your answer might be yes or no. That's a binary answer, right? Then the next question is, how confident are you in that answer? So it depends. It depends on what you did to actually give me the answer. So if you looked at it in terms of, you went to Met Service, you looked at it, you ask Google, then you might say, I believe I'm 99% confident because 99% of the time it's always right. And there's 1% that it doesn't get it right, or something like that. If you've not actually referred to anything, you might say, yep, I'm confident up to 50%, because that's as good as a random guess. So now, how does that translate to us looking at the errors within the model? So you can actually, in some of the models, you can actually have look at the probability of the predicted distribution of the labels. And you can get that from neural networks. So that would be the probability distribution in the activation layer, softmax layer. Or if you're looking at naive Bayes, it's the probability distribution that corresponds to the posterior probability of the labels. So typically, how does that impact your drift detection? So on the left-hand side, let's say we have our 5 triage priorities. And typically, the document was triage at triage at 3, but the system said it was at 2. So you got it. The system got it wrong. It got it wrong slightly, because it wasn't very confident specifically. Now, same case. We got it, the clinician said it was 3, but the system said it was 2. This is a stronger indication that something went wrong. So that's a stronger drift detection right there. So now, the question now is, how do we use this type of information to predict when changes happen? So specifically, what we can do is that instead of using point prediction, we might be able to use how confident we are in that model. Why is this important? It's important in two ways. If we actually don't do it, what might happen is we might actually get into a situation where virtual drift actually mimics real drift, where you might have an increase in errors or a decrease in accuracy, but realistically, it was a shift within the frequency of occurrence of that doesn't impact the decision boundaries. So an example of that is that if the rate of condition which priorities is hard to predict increases, then what happens is your accuracy will generally decline a little bit. So if you put a normal drift detector in, it will say retrain. But retraining at that point doesn't gain you very much because the boundary hasn't shifted. So it's an expensive operation for not a lot. So in terms of what we decided to do is that we wanted to actually be able to distinguish between virtual and real drift. So when we talk about distinguishing it, we came up with this technique called calibrated drift detection method that detects the calibration of the base learner rather than changes in accuracy. This requires the learner to predict a probability distribution over the labels itself rather than making a point prediction. What do I mean by that? So imagine you were going to the races. You would place a bet on a horse, and there would be certain odds there. Same thing here. So the model bets on a prediction. And at each time steps, you get a net payoff. So if your prediction was correct, you get a payoff of 1 minus how hard it was to actually get the prediction. If it was wrong, then there's a penalty, a negative of that particular confidence that we're looking at. So we keep a sliding window of that information right there. And when we talk about the sliding window, what we do is we monitor that. And when we monitor that, we sort of say, right, if and we put this particular sliding window through a bound, and if it's below a specific threshold, we say that we have to retrain the model. There is an actual drift that's occurred. This particular bound right here is actually the Hofting bound. So it's a very common bound that's been used in this in data stream to actually monitor changes. But it's been adapted to actually allow us to look at the payoff penalties. So what we have is we are using the drift detector on and using the calibration to differentiate between real and virtual. The only caveat with this whole entire system is that it needs the model that we're using to be calibrated. So when I mean by calibrated, it means that if it's been calibrated to 90%, it means that if you had 10 observations, you get 9 of them correct, 1 of them might be wrong. So it needs to be calibrated. So we've seen cases of where how shifts have happened, with different types of shifts. We've looked about how to monitor them. We looked at one classical example of an online update. We've seen some of the things that was one research that we're currently doing. And now is my question to you guys. If you wanted to model a data set, how would you model this particular data set? And this is a real data set. And this is a data set of air pollution. And this air pollution is collected from a sensor from LAWA and between October 2019 to October 2020. The sensor sits right in the middle of Queen Street, right here. And what we have is on the graph right here is you've got the concentration of air pollution, and that's the dates that we have. And when we look at it, how easy is it to model this? And you quickly realize that there's a lot of things that we have to adapt to. So, for example, there are a lot of catastrophic events that will actually mess with your model, and you have to actually constantly adapt it. When to adapt and when not to adapt. For example, this peak right here, if everybody remembers what happened in October last year, the Sky City Convention Center was burning. And then we had the Australian bushfires that messed with our skies a bit. And then we had lockdown 1. So we noticed that if I asked you to model this, how would you go about doing it? It is a hard task, and there's different decisions that you have to make to model these kind of changes. So as a Greek philosopher once said, change is the only constant in life. And at this point in time, I think making sure that our models are accurate, and ensuring we understand how to maintain these models, to maintain veracity and the efficacy and accuracy of these models is important. So with that, I'd also like to thank the school for inviting me here, and also I'd like to acknowledge all my students and my collaborators. Thank you so much for your time.
Playing over time for question now. So any question from the room?
With a lot of this data, once you've trained your model and you've got the new data coming in,
Yep.
very hard to get any ground truth.
Yeah.
So you don't know whether you've got your prediction right.
Yeah, you don't know really whether you got prediction right. And that's actually a real problem in data streams. With our case, you can get the ground truth later on because there's always an expert that actually tells you whether you're right or wrong. But you're right. It's an absolute real world problem that we have. There's a lot of research in the area that talks about delayed labeling. How do we actually effectively maintain the models? And if we have labels later on in time, how do we actually retrain? And how do we actually get back to the point of when it actually shifts and what we actually have to do? There's the other ones that we have, things like active learning and semi-supervised learning, where we go about we're trying to actually impute what the value should be, and then you have at certain points you need to actually get expert to say, at this point I really need you to actually give me some input to tell me whether I'm on the right track or not. So there's a lot of research in this area, but I completely agree. This is an open research question, and it's one of the things that we are concerned about, and there's a lot of research going on in this area as well. You're asking the question of how long does it need to actually train a model, basically, right?
Yeah, to
Predict.
whatever the new
Normalist. All right, okay. That really depends on how difficult. The question now is how difficult is it to model? What are you modeling and how difficult it is to model? Because if it's something fairly simple, then you actually can get quite a good model within a very short amount of time. Like how long, and the answer normally is it depends. Because it really depends on the type of data, how dirty the data is, and there's various factors as well. It's really hard to actually give a number on that. But there are different ways that you can actually see. You can actually train it, and you can actually, there's different testing that you can actually do to ensure that your model is valid. So things that we do that typically is not done in normal machine learning, we do something like frequential testing, where what we do is we use the data to test, and then we use the data to train, but not the other way around.
How much complexity can you handle? Like biological systems have many variables interacting on many different levels, with combination, permutation, all those sorts of things. So in the real world, can you crunch really difficult biological models?
Okay, that's a very good question, and that question really is sort of pushed onto the model itself. It really depends on what type of data we're dealing with. And if we're dealing with something like a really, like things that are high dimensionalities, or things like if you're talking about, all right, I need to process data for driverless cars or things like that. They are more of, they can be construed as a very complex system where what you're building, the model that you're building, needs to be able to handle that. So specifically, it really depends on what the model you're using. If you're using a deep learner, then potentially it might be able to do that. I wouldn't want to say yes or no, but potentially. It depends on what is the underlying classifier that you're using.
But even with the car model, for example,
Yeah.
There'd be lots of different variables that would go into that,
Yeah.
right? So how do you kind of decide what data feeds into that?
Right. So how do we actually decide what feature vectors we're actually using?
Yeah, what even is the input data to decide on that car?
That's kind of that's a good question, and that's kind of a question of what type of feature selection is important, what type of features that will actually impact your model itself. So the question is, this question is sort of fundamental to machine learning. Is pretty general in terms of it has the same weaknesses. We need to be able to actually come up with the right feature space to model the data. And if you don't, it doesn't really work very well. But you can do different feature selection techniques and apply that before you build your model to actually ensure. Yeah, you could. There are different things. There are even things that you can do is like, oh, are the features drifting themselves? And you can actually analyze that. You could actually have a post hoc analysis, but that's kind of slightly different context. Yeah, it's a good question.
What sort of data sets do you use to test your algorithm? What sort of problems spaces?
Yeah, good question. Really good question. So there's lots of data that you can actually try this on. So one of the specific things that we're looking at the moment is we're looking at patient data, triage. There are other things that other people in this room are doing, which is they're looking at sensor data for air pollution. So there are lots of data that you can actually use. And intuitively, you can actually see if this is a streaming data of some sort, potentially you can actually use it on the system. It depends on how you model. It's all a question of how you actually set up the model and what are you modeling.
Would you normally program kind of
location of each vector to say this is outside the range of our model, therefore we shouldn't predict.
Ah, okay. Right. So you're kind of saying if it doesn't fit within the parameters, instead of giving it a prediction, you're saying I don't want to deal with it.
Yeah, there's a classic case of the accident that killed a woman in driver's car. She was walking across a 4-lane highway with a bicycle in rain with a very long raincoat.
Okay.
And the code just didn't identify
Ah, okay.
what it was and didn't do any emergency stopping.
In terms of, you're sort of saying if you're not certain, instead of giving a prediction, don't predict, basically. I can understand that there is it's kind of like, okay, you want to put things in the I don't know bucket rather than saying that there is a prediction, but of a confidence, basically. That's actually an interesting point, because I've seen research out there that actually have done this. I myself haven't actually explored this very much. But there is something to be said about, it really depends, exactly as you said, what is the impact of that particular model? How critical is it? How critical is it to actually have somebody step in and say, look, we don't know, can somebody take over? And that's true. Yeah.
I just got an email to say that Tess was about to release their self-driving car.
Cool.
Okay, so there are a couple on Slido. Is drift detection a specialized version of causal inference?
All right. Is it a special case of causal inference? While it can be used, drift detection is. It can be used for causal inference to actually detect whether there's a shift there. What I would say is drift detection is more of, it doesn't have to be used in causal inference. It can also be used in things that we do actually use it in unsupervised learning as well. So there are things like feature drifts. There are things that are, when we're drifting, we're actually looking at drifts within what we call it, some of the underlying individual features, but we're not really using it to actually do any causal inference. You might want to actually do things like virtual drift when we're actually dealing with it with independent variables themselves, because that sometimes is interesting.
Question number 2.
Is there something specific about random forests that makes them work better, the drift detection or adaptation? Or will speculative adaptation work elsewhere?
The reason why I talked about random forests is because it is a very interesting approach. While it is from the message that I was trying to actually give was mainly about how we adapt it online. There are various techniques that you can still do online adaptations for, and but I just chose random forest because it was interesting. Yeah.
Interesting topic. In 1964, I got asked to do a statistical analysis of the forests that had been planted in the North Pole. And one of the things I asked was there enough statistics to make this valid, the analysis valid? And one of the complexities was that the practice was a small number of trees are what they call elite. They are significantly bigger and better than other trees. And obviously you want to plant the seeds from those.
let's put our hands together and thanks to
Thank you.